We're starting lesson 1.7, and we just left a lesson where we were solving systems of equations, and we had three different methods. We solved by graphing, we solved by substitution, and we also solved by elimination. So now we're going to be solving systems of inequalities using the graphing method, and this will be a review. We're going to look at some problems in the beginning that are going to be pretty easy just to refresh your memory a little bit. But the solution to a system of inequalities, if there is a solution, will be indicated by shading a particular region, and that region represents all of the ordered pairs that would make the two inequalities that are contained in the system would make both of them true. So we're talking about all of the xy coordinates from ordered pairs that would make the system true, and we indicate all of those by shading the region that represents basically the solution to both of the inequalities. So let me show you what I mean with this example. So real simple example here, we're going to first of all sketch the boundary line for this inequality. Think of it as y equals 3x minus 5. So I'm going to go to negative 5 on the y-axis, and then slope of 3, up 3, right 1. And this is going to be a dotted boundary line. Okay, so we've sketched out we got the y-intercept, we've got the slope, a couple of points. This is going to be a dashed boundary line. So I'll change my line draw tool here. So the boundary line would look like this. And I typically, when I'm solving these systems, we're going to have two boundary lines, and each one of them, of course, is going to be shaded. And I typically will wait until both of these are drawn, and I just do all my shading at once. If you would prefer to go ahead and shade as you go, and then overshade the part that would represent the solution, that would be okay. But if I were shading, the greater than side, of course, for this dotted boundary line would be this upper side, the side that contains the origin. Again, if you wanted to test the origin, 0 plugged in for y, and for x, you would have 0 is greater than negative 5, which is true. So the origin should be on the shaded side. But I'm going to do it like this. Now let's change colors, and we'll do a boundary line of y equals 4. And of course this one should be solid. I have to change that. So here's my boundary, y equals 4, and then we would be shading the underside, the less than side of this horizontal line would be the underneath side. So putting these two shadings together, that represents the solution to the system. So the greater than side for the blue, of course, would be the upper side. We already talked about that. But we need to combine that with the shading for the other inequality, y is less than or equal to 4. The less than side for the red line would be below. So the solution is indicating where these two shadings collide. Okay, greater than for the blue and also less than for the red. So we're talking about this area that I'm shading in yellow. Any ordered pair that you could pick out of this shaded area would be a solution to the system. And remember, a true solution not only makes the blue inequality true, but it also makes the red when we plug those values in from those ordered pairs out of the yellow area. Okay, so that's a pretty simple example of how to solve a system of inequalities. So let's just take another similar example, and then we'll move on to a few more challenging problems. I'm going to go ahead and solve for y in the blue here. You could solve, or you could graph this by intercepts if you choose. And it would be okay. You wouldn't have to worry about the inequality changing because we know that the y coefficient is positive. So if you wanted to just think of plotting intercepts and graphing, that would be fine. I'm just going to go ahead and solve for y, adding 2x to both sides. And then one more step, dividing by 3. Y is less than or equal to 2/3 x minus 8. Okay, so let's plot the blue boundary line, and then we'll do, or think about, the appropriate shading. -8 y-intercept down here, and then 2/3 slope up to right 3, up to right 3, solid boundary line, making sure it's blue, solid, okay, 2, 1, 2, 3, get a head start, and there's my boundary line for the blue inequality. And when I shade the less than side, which is what this indicates, the less than side will be under here. Okay, so now let's work on the red. It's already solved for y, which is nice, so I just plot -1 y-intercept and a slope of positive 2/3. Well, you probably already recognized when we got to this point that these are going to be parallel lines. We still need to show the graph. So we're going to go up to right 3, go down to left 3, solid line. And that boundary line looks like this. Okay, well, these are parallel. It could be, I mean, just because they're parallel, and if this were a linear system, this would be no solution. But since it's a system of inequalities, again, we're worried about where if the two shadings, the red and the blue shadings, do they come together? Do they mesh? And you'll notice that in this case they do not. The shading for the red, greater than, would be above the line for the red. And then for the blue, it's going to be less than, which is below the line. So once again, since we're interested in where the two shadings come together, what area do they share? Well, that doesn't happen. These two shadings obviously never meet, so therefore we would interpret this as a no solution. So I don't want you to think that because they're parallel, they're no solution. It just happened to be that the shadings for the two separate inequalities did not collide, they didn't mesh, and that's what makes it a no solution. Okay, so another, oh, and by the way, don't worry about these problems. This is from old slides, so you have those on your notes, so you can just mark those out. I will update you on what you'll be doing. In fact, you already know it's on your last slide. So just ignore references to problems. So here we go. Let's try this a little different. It's just 3 inequalities that need to be graphed, and it's going to form a triangle, and we'll be shading based on these inequalities. So if we do it right, we'll be shading inside the triangle, and then it's our job to identify the vertices. That's those 3 points on the outside of the triangle. So here's what that looks like. I'll do that first one, the first inequality in blue. The boundary line x equals 4 looks like this, and it's going to be solid. So here's x equals 4. And once again, if I were shading, since this is a vertical line, the less than side would be on the left of that line. Okay, we'll just do this one in red. So we can color code just a little bit. This has a y-intercept, of course, of 12, 2, 4, 6, 8, 10, 12, and a slope of -3, down 3, right 1. And this is going to be a dotted boundary. Okay, So it looks like that. And we'll be shading the greater than side. So if we stopped right here and did just these two, we would be shading this region right here to the left of the vertical blue line and above or to the right of the dotted red. All right, and now let's add that final boundary line. We'll do this one in green. The boundary y equals 9, 4, 6, 8, 9, and it's going to be solid. Okay, so there's the boundary. So you put all the shadings together. Where do they all come together? And below, or to the left of the blue, below the green, we already talked about above to the right of the red. So we have this triangular region. And this is going to be a good little preview for our lesson on linear programming, because those graphs look a lot like this. And we're also going to be naming vertices. Okay, vertices are, in this case, these 3 points where two lines intersect. So we have this point 1, 9. It's a vertex. We have 4, 9. And then we've got this point down here at 4, 0. All right, so we've basically finished this problem. We've named the vertices, and you've got a couple like this that you will be doing. And let's try this one. So you have choices here. If you would like to graph by intercepts, I think that's what I'm going to do because the y-intercepts are kind of large. So and we're not going to have to worry about switching the inequalities. We don't have to solve for y with the fear that, well, maybe the inequality will change because we'll be dividing by a negative number to solve for y. Well, all of these y coefficients are positive. So for that reason, I'm just going to graph these boundary lines by doing intercepts. All right, so I'll just start here. The x-intercept, to find the x-intercept, I'm going to divide by 19. So let's grab my calculator. 74 divided by negative 19 is negative, I'm going to call that negative 3.9. So I'll just say x-intercept, negative 3.9. And y-intercept, we'll divide by 8. 74 divided by 8 is 9 1/4. Okay, and this is going to be a dotted, dashed boundary line that should cross these 2 points real close to negative 4. Just about negative 4 on the x, and then 9 1/4 on the y. 2, 4, 6, 8, 9, and we'll call that a fourth. So because we're making estimates, I'm going to allow a little bit of leeway, and you'll see in just a minute. I'm trusting that my lines are going to intersect according to what the book says, but it's not always possible, and we're not doing graphing calculators, so I'll explain when I get to the end when we're ready to interpret our answer. So let's see if I can connect these two blue dots with a dashed line. Give it a shot here. Yeah, it's not real good. Okay, yeah, it looks pretty good. Okay, so took care. I think I might extend this just a little bit because I might need that to be a little longer to give it a chance to intersect with another line. Okay, that's good. Maybe I'll do this one in red. And so the same thing, let's get the x and y intercepts. X-intercept, I'm going to divide 119 by 26, and I get 4.6. y-intercept, I'm going to do 119 divided by 38. And I get 3 point, I'm going to call that 3.1. I'm using a broken calculator, so the numbers don't show up real well. 3.1. Okay, let's go and plot those. So x-intercept, just a little bit more than 4.5. And we'll put it right there. Y-intercept, a little bit higher than 3. And then this is going to be a solid. Let's see if we can hit these. Nope, I didn't hit them. So you won't have any trouble with this. I'm going to pause this, and so I won't take up a lot of your time. Okay, I think I got it. And now we'll work on the final one, and we'll just do this one in green. Okay, so to get the x-intercept, let's do negative 198 divided by negative 12, 16.5. And the y-intercept, negative 198 divided by 54. And about negative 3.7. Okay, so 16.5 goes beyond, I think I have 14. 1, 2, 3, 4, 5, 6, 7. Yeah, I got 14. I'm going to call this 15, 16, and then I'm just going to do a half. Again, this is going to be kind of rough, and we'll see how close we get, but I'm going to allow you a little bit of leeway on these. So the y-intercept, negative 3.7, 1, 2, 3, pretty close, down closer to negative 4, and then once again, I'm going to try to line those up with a solid green line and see if I can connect those points. Okay, I think I got it. Making sure I've got the correct dotted line and then the two solid lines. This is my triangle, and if we were to do the shading correctly, we would be shading in this area, of course. We're just going to shade the actual triangle region. Less than the blue is underneath, less than the red also underneath, and then we're doing greater than the green, which is above. And we want to know where all three of those shadings collide. Now this is where you may be a little bit off. I hope you're pretty close, but I'll tell you what the book says the vertices are. Looks like I'm right on one of them. One of the vertices is negative 6, negative 5. 2, 3, 4, 5. Right on that one. Okay. Another vertex is supposed to be negative 2, 4.5. 1, 2, 3, 4. That one's a little low. It's pretty close. But if you're in the neighborhood like this, like I am, I'm not going to mark that wrong. Okay, and then the other one is supposed to be 7.5. Yeah, this one's more. 2, 4, 6, 7.5. Oh, it's pretty close. Negative 2. It's a little high. 7.5, negative 2 is where it's supposed to be, but I'm going to consider that really, really close in the neighborhood. So even though I'm off just a little bit because we're approximating where these x and y intercepts are, we're still pretty close. And that's the kind of thing I'm going to do for you as well when you do these problems for your assignment. Okay, so that's the answer to one like you're going to do on page 55. Okay, let's take a look at absolute value inequalities. Let me give you a formula that's going to be really handy when it comes to graphing absolute value, whether they're equations or inequalities. Remember, I think I've already shown you this, but if you spell the words absolute value, always remember that the result of the graph of an absolute value function has to be a V-shaped, whether it's upright like this is, or if there's a minus in front of the absolute value, then it's going to flip the V over. So we know that this is going to be an upright V, and a key point to sketching the graph of this V is, first of all, locating this point that's called the vertex. And I'm going to give you a formula to help you find the vertex for this absolute value boundary line. Okay, the formula looks like this. It's let me give you some letters and then I'll explain where the letters come from. The opposite of B over M in C. The vertex, of course, is going to be an ordered pair. This is how we'll find the x coordinate of the vertex, and then this number C is the y. Well, you've got to know, where do we get these numbers? So if you look inside the absolute value walls, the number in front of x is m. That's familiar because we're used to seeing y equals mx plus b. Okay, so once again, still within the absolute value walls, this number being added is called b in our formula. And then we've got this number. Sometimes, if there is no number, it's understood to be 0. But in this case, we've got this number outside the absolute value walls, -4, and I'm going to label that as C. So if you know how to identify the number in front of x is m, this other number, it'll always be inside the absolute value walls. If there isn't anything added or subtracted, then b is understood to be 0. And then this number outside will always be the y coordinate. So the opposite of b, which is 9, over m, which is 3, that's the x coordinate, and then the y coordinate will be -4. So simplifying, we've got -3, -4 as the vertex. -3, -4. Okay? Now, I think I mentioned earlier, if since there is no negative in front of the absolute value, we'll talk about this more later, but with a negative, it would make my V open down. But since it's positive, I know that my V is going to open upward from this point called the vertex. So how do I get the rest of the V? Well, there's two different ways. Maybe you learned in Algebra 1. Here's the way that I like. We know that this has to be the very bottom part of the V, the vertex. So look at the slope. It's 3. So from this vertex, let's count a +3 slope. Up 3, right 1. And I'm going to do that one more time. Up 3, right 1. Well, obviously, this would result in half a V. And a V, or an absolute value function, is really 2 lines. And where those 2 lines intersect is the vertex. So to get the other half of the V, just think of a -3 slope. Up 3, left 1. Okay, and once again, this is going to be a solid V shape because it says we're equal to. So I'm going to draw my V. And I'm going to wait and do shading at the end, but if I am shading the greater than area for the V, just think above both of the lines, we're talking about this area inside the V. Okay, so let's go ahead and I'll do this in blue. Maybe we can just go ahead and solve for y. All right, so here we have a y-intercept of 7. and we have a slope of negative 1/2. So down 1, right 2, or up 1, left 2. And this is also going to be a solid line. Okay, so I have my two boundaries, and now I'm going to do the proper shading. So less than the blue, but greater than for the absolute value v, which we've already talked about, will be inside the v. So essentially we're talking about all of the ordered pairs that would fall in this region. Okay, below the blue, and then also within, contained within the red V. And that will be my solution for this absolute value, this system that contains one absolute value inequality and then one regular linear inequality. Okay, I thought I would set you up with this one, and this will wrap up the lesson. I thought I would just give you the inequality and then see if you can take it from there, and we'll see in class how you did with it. All right, so this guy Steve, he's trying to decide what to put on his smartphone. It's either going to be audiobooks or songs. So we're given some information about costs for each. We're given some information about how many he wants of each at the most or at least. So the bottom line is we're trying to figure out the possible combinations of songs, books and songs that he can have. Okay, so I'm just going to let x equal the number of songs. We're dealing with two different quantities here, two different entities, items. We're dealing with songs and audiobooks. So if you switch these, it would be okay. X will be the number of songs, Y will be the number of audiobooks. So I'm going to come up with the system, and then I want you to see if you can graph it, and then we'll talk about possible combinations of books and songs that he can have. All right, so let's think first of all about what he says about how many of each he wants. Let's think about the audiobooks. He wants no more than 4, so 4 at the most, but he wants at least 1. Okay, no more than 4 audiobooks, but at least 1. So using y as our variable for audiobooks, we can say basically he wants between 1 and 4. Okay, he wants at least 1, but he doesn't want more than 4. Okay, so what about songs? He wants at least 10 songs. Okay, so his number of songs will be greater than or equal to 10. All right, we're also told some information about how much these cost and how much he has to spend. So that's kind of a clue that this sentence needs to be turned into an inequality. The books cost 15 each, and the songs are 95 cents each. So let's just go with songs first. 95 cents times every song plus $15 times every audiobook, and he only has $63 to spend. Okay, so in inequality form, we're going to have to say less than or equal to 63. Cannot go over 63. He can go to 63, but not more. Okay, so this is your system. So what I'd like for you to do is, before class tomorrow, see if you can go ahead and graph these 3 inequalities, do the appropriate shading. One thing I will want to stress is when you graph these systems of inequalities that are based on real life situations, it's very typical. I'm just going to do a rough sketch here. It's very typical because we're not dealing obviously in negative quantities. Everything all of our shading, everything that we do is going to be in quadrant 1. And then something else that I want you to pay attention to, it's always important when you're doing these graphs, again, that describe real-life scenarios, make sure that however you define your variables, and we would have been okay if we had switched these, you know, as long as we set it up properly, of course. But make sure once you've come to a conclusion about what your variables are going to be, then you label your axes accordingly. Okay, we want to make sure that our graph makes sense to anybody who's looking at it. Okay, so that should take care of our notes. And go ahead before you come to class tomorrow and see if you can bring this problem to its conclusion. And then we will work on the assignment. We're going to flip the classroom, so don't worry about doing any of the other problems on the assignment. We're going to save those for tomorrow. And if you have any questions about these notes, feel free to let me know.